In the last video, we discussed how to recognize acetal and hemiacetal functional groups, which are important in carbohydrate chemistry, such as the understanding of glucose and other sugars. In this video, what we are going to look at is how we use aldehyde and ketone reactants reacted with alcohols in order to give hemiacetal products, which have the functional group that we see here in gray, where we have a carbon that is part of an ether group where we have an O-alkyl group bonded, and that same carbon is also directly bonded to an OH group or an alcohol functional group. So a hemiacetal has an OH group and an ether group directly bonded to the same carbon. Let's talk about how we go about creating that functional group in a reaction product by starting with an aldehyde or ketone reactant. So the general equation here that we will explore is that an aldehyde or ketone reacted with an alcohol will give us as the product a hemiacetal functional group. I am going to go ahead and put this as an equilibrium arrow rather than a reaction going exclusively in the forward direction, because in reality this reaction is reversible, and as we will see a few videos down the road, this reversible reaction is important in the different forms that sugar can take within the body. So reacting aldehyde or ketone with an alcohol gives a hemiacetal. The general way that this works, or the general layout of this reaction, is we'll start with our aldehyde or ketone reactant, which I'm going to plug in R groups here that I'm going to call R and R prime. R and R prime represent carbon and or hydrogen, depending upon whether this structure is an aldehyde or a ketone to fit one of those two functional groups. We react with an alcohol, which I will call R double prime, to distinguish that this carbon chain or ring is not necessarily the same as the two here. It could be the same, but it doesn't have to be. And since it's an alcohol, that carbon chain or ring is directly bonded to an OH group. And what happens in these reactions, I'll show my equilibrium arrow here, is that the alcohol is going to add across the carbon-oxygen double bond here. So when we talk about addition reactions, we talked about this previously with carbon-carbon double bonds of alkenes, and we showed that two groups add across the carbon-carbon double bond to give a product that has just a carbon-carbon single bond. Analogously here, this carbon-oxygen double bond will become a carbon-oxygen single bond, and the groups that are adding will add here and here during that process. During the process, what's going to ultimately happen if we dissect the destination of all of the atoms here is that the oxygen of the carbonyl group ultimately becomes, in the product, the hydroxy group of the hemiacetal. On the other hand, the carbonyl carbon right here becomes directly bonded to the O-alkyl group of our alcohol. So this oxygen that's bonded to the R double prime group right here is what will become bonded and add right here at the carbon of the carbonyl. So we end up ultimately, as a result of these reactions, taking this O-alkyl group from here, from our alcohol, and that gets plugged onto the carbon atom right here of our carbonyl. The net result of this is that we end up with our R, and I'm color coding this the same way that it was originally. In red was what originated from our aldehyde or ketone. And then in blue is what became our OH group. And then in green was the O-alkyl group donated from the alcohol molecule. So I put that in as O-R double prime, where R is a carbon chain or carbon ring. That structure here that I'm highlighting in yellow corresponds over here to the O-R double prime group from the alcohol, and hence was what bonded here at the carbonyl. So the pattern is always the same. It's always going to be that the oxygen atom of the carbonyl becomes an OH group. The carbonyl carbon is always going to bond to the oxygen and the alkyl group from the alcohol to become OR double prime here in this general template example. So thinking of this in the perspective of functional groups, what we need to remember is that the reaction of an aldehyde or ketone plus an alcohol will give us our product here that we refer to as our hemiacetal functional group. It's a hemiacetal because we have a single carbon atom right here that's directly bonded to an OH group, and that same carbon is directly bonded to an ether group as well. Let's tackle this a bit deeper. We can look at how this reaction occurs, and the reaction occurs through what we call a reaction mechanism. A reaction mechanism is the series of electron steps that we take to go from the reactant to the product, because ultimately chemical reactions are not magic. They ultimately instead involve a series of electron transfer steps to go from starting material to product. We can write out a simplified mechanism for this reaction by taking, if hypothetically we started with benzaldehyde, remembering that benzaldehyde is an aromatic molecule directly bonded to an aldehyde group, like so. And we react that with methanol as our alcohol, recognizing that the reaction of an alcohol plus an aldehyde is expected to yield a hemiacetal product. We can think about what's going to go on here in order to yield that hemiacetal product. Electrons are what do the work in chemical reactions, so I've drawn in the electrons explicitly here. Even though I haven't drawn complete Lewis structures, I have shown the electrons explicitly. And to illustrate what happens here, the oxygen atom would be expected to have a negative polarization because oxygen is an electronegative atom, more so than the carbons and hydrogens that it's bonded to. And negatively polarized atoms, such as oxygen, are drawn toward positively polarized atoms, such as the carbonyl carbon here is positively polarized. Opposites attract, for better or for worse, much in life. And so the oxygen atom that is negatively polarized comes over here and is attracted to the carbon atom. We show that attraction and interaction by using an arrowhead to indicate that the electrons from the oxygen travel over and they are going to form a covalent bond to this carbon atom. If that was all that was going to happen, was that they would form a covalent bond here, this carbon would end up with 5 bonds to it because it already has 4. If it made a 5th one, that would be over the octet rule. We never do that. And so what happens at the same time is that electrons from that pi bond flow up onto the oxygen atom so that we can avoid going over the octet here at this carbon. Our so-called electron pushing arrows, those arrows that we just drew to illustrate what's happening, we can show what results from those electron pushing arrows by sketching it out here. We made a new covalent bond that I will show in red between the carbon atom that was here in the center to start with and is here in the center as well. That new carbon bond came over here to the oxygen atom in our map, our electron pushing arrow. So we show an oxygen atom down here directly bonded to a hydrogen atom. That was the hydrogen right here. I'll show a line going to that, and directly bonded to the CH3 group of methanol. So everything that I have highlighted in yellow here on my reactant side, CH3OH, is everything that I'm highlighting in yellow on the product side over here, CH3OH. We used one of the 2 sets of lone pairs. There's 2 sets of lone pairs here and here. We used one of those 2 sets to form the covalent bond over to the aldehyde molecule. The other lone pair, nothing has happened to, and so that would still be hanging out. If we calculated the formal charge on this oxygen atom, we would find that it would be +1. And we would find additionally that we haven't drawn quite everything in yet here because our carbon atom that we highlighted in blue over here on the reactant side, and I'm showing with my laser pointer right now, would become a carbon-oxygen single bond because we took the pi electrons and put them up onto the oxygen. So we show that oxygen up here. Pi bond is no longer there because the pi bond has gone up onto the oxygen, so that this carbon avoids going over the octet. As a consequence of those pi electrons moving up onto the oxygen would have not just 2 sets of lone pairs like I had to start with, it would have a 3rd set because the pi electrons had to go somewhere. They go up onto the oxygen atom. So rather than having 2 sets of lone pair electrons, there would be a 3rd set there, which I'm going to draw in red there to illustrate their origin was these electrons flowing from the pi bond up onto the oxygen. That would give this oxygen atom a negative formal charge if we did our formal charge calculation because the oxygen has 3 sets of lone pair electrons and 1 covalent bond. So this is our intermediate in this reaction as we head toward the final product. Then what happens next is, in order to get to a final product that has no formal charges on any of the atoms, what we do is we do a transfer of a proton. So this represents what we call an acid-base reaction, where the oxygen having a negative charge acts as a base, and it grabs this hydrogen from down here, and that breaks the oxygen-hydrogen bond and sends those electrons onto the oxygen atom. And so as a consequence of that, we'd still have our aromatic ring, still directly bonded to our carbon, which I will highlight for us in turquoise because we've highlighted it in turquoise before. That carbon atom is now directly bonded to an OH group. 2 sets of lone pairs hanging out there because 2 sets of lone pairs here in red up top and here did not react. The other set over here came down and formed a bond to a hydrogen atom, so I'll show that in green there, that we formed a covalent bond there. The hydrogen atom that's out here to the right is still hanging out there, so I'm just going to sketch that in. Nothing's changed there. And then we come down below, and we had a CH3OH. We lost that hydrogen there because it got transferred up top, and so we have an OCH3 now down there in the bottom part of the molecule. So I'm going to draw OCH3 here. There would be 2 sets of lone pair electrons, because we had 1 set originally there in red that I'm highlighting. The second set came from breaking this oxygen-hydrogen bond. Those electrons from that bond had to go somewhere, showing the arrowhead indicating their destination. They went on to the oxygen atom here. So in this product, what we see, and I will highlight in red here, is we have our hemiacetal group. Oxygen directly bonded to a carbon, directly bonded to an ether group, makes for a hemiacetal. So this is one way that you can work out how to go from the reactants of an alcohol and an aldehyde or ketone to the product, is using this so-called reaction mechanism where we sketch out the electron transfers using these arrows to indicate what's happening. That is one way to work through logically determining what product would result from these reactions. The other route that you can use for logically determining what would happen from these reactions is instead to use the approach that we've looked at up here, where the template and pattern is that you take an aldehyde or ketone starting material, react it with an alcohol to give a hemiacetal product by just converting the carbonyl oxygen into OH, converting the carbonyl carbon into a direct bond to the O alkyl group from the alcohol to give us our final product. Either of these approaches are perfectly acceptable for purposes of this class. In this class, you will be expected to be able to take an aldehyde or ketone reactant, react it with an alcohol, and predict what hemiacetal product would result from that. You will not be asked in class to show this reaction mechanism for accomplishing that, but if that helps you in seeing how to get to the final product, that's certainly an acceptable way to go about it. So generally, one of these 2 strategies will make the most sense to you in predicting the product of the reaction. And I don't care which of these 2 approaches you take. The main thing is that at the end of the day, you are able to predict what product would result from the reaction of an aldehyde or ketone with an alcohol and draw out the hemiacetal reaction product. In the next video, we will go through some example problems where we look at predicting the products of these types of reactions and other reactions such as oxidation and reduction reactions that we've looked at for aldehydes and ketones.